What would 3D printed habitats on Mars look like? LavaHive is a Mars colony made from the planet's own sand and dust, inspired by centuries-old construction techniques. Such in-situ resource usage allows for huge reductions in the mass and cost of a journey to Mars. Both NASA and ESA have expressed interest in using this technology to achieve their goals. In recent years, both commercial and public interest in additive manufacturing has grown. A plethora of disruptive business applications have already been shown using 3D printing, and many more are expected. Now, teams from all across the world have been inspired to create a 3D printed Mars dwelling for a NASA competition. Hey folks, and welcome to Next Tech Ventures, where today, in the next few minutes, we are going to discuss everything in depth about Mars 3D print habitat. So are you guys excited? Without any further ado, let's jump right into the video. So, how to 3D print a habitat on Mars? 3D printing has been a process since antiquity, when huge constructions were produced additively, layer by layer. We have just lately integrated the process with robots and computer control, allowing us to 3D print objects of practically any shape, utilizing a varied spectrum of materials ranging from metals to plastics and even ceramics. Certain complex shapes that were previously difficult to create using traditional manufacturing procedures are now possible using 3D printing methodologies. There are various benefits, including reduced logistical requirements, material utilization, and manufacturing time. And product applications are diverse, ranging from lightweight specialized aircraft engine parts to the construction of entire concrete dwellings. The space agencies recognize this technology's mission-enabling potential. Under its General Studies program, ESA commissioned research in 2013 to evaluate how 3D print technologies could be used to create a dome-like structure for a lunar facility, sheltering humans from the harsh radiation and micrometeorite impacts on the Moon. It is feasible to significantly reduce the mission's bulk and expense by exploiting local resources to create essential mission pieces rather than sending them from Earth, a technique known as in-situ resource utilization, or ISRU. The sub-habitats are work areas with 3D printed walls made of Martian sand and dust. NASA is also investigating the feasibility of employing 3D printing on space missions. It announced the 3D Printed Habitat Challenge in March 2015, which is accessible to participants from all over the world. Teams proposed an architectural proposal for a 3D printed Mars base with the goal of simulating the development of technologies required to additively create a habitat using ISRU and spaceship material recycling. It's a NASA CENTENNIAL Challenge, an incentive reward presented to produce disruptive solutions to NASA-interested problems. NASA intends to collaborate with non-traditional sources, such as the global maker community, enthusiasts, and entrepreneurs from the general public who have championed 3D printing technology and its applications. Inspired by an earlier ESA study on lunar 3D printing, a team of European Astronaut Center and Liquefier Systems Group of Austria members collaborated to propose a concept for this Centennial Challenge. The team was chosen as one of the top 30 ideas from over 160 submissions and has been invited to exhibit their proposal at the World Maker Fair in New York. Architectural inspiration. The LavaHive design demonstrates the unique possibilities of additive manufacturing technologies for future exploration missions. The feedstock material employed as raw material for the 3D printing process in the proposal is Martian regolith, a catch-all word for the loose sand and dust abundantly available on Mars' surface. Significant mass savings can be gained by employing this indigenous material to create structures and shelters, resulting in a reduced logistical supply burden from Earth. The LavaHive concept is a revolutionary hybrid method. It is constructed out of an inflatable central habitat with 3D printed reinforcement walls, as well as a network of interconnected sub-habitats composed of sintered and molten Martian regolith, as well as recycled and repurposed spacecraft parts. Sintering includes the use of heat and/or pressure to fuse particles, and its practicality with regolith has been proved in a number of operations on Earth. LavaHive is a modular concept for a 4-person crew mission that may be expanded or adapted to changing mission objectives. In its original state, a hybrid inflatable 3D printed main habitat is linked to 3 or more sub-habitats via central corridor. The main habitat houses the crew's living rooms and is linked to the sub-habitats by 3D printed corridors. These contain a laboratory, a greenhouse, a garage airlock, and other necessary working rooms. A hybrid method with purely 3D printed sub-habitats coupled by a central inflatable habitat supplied from Earth makes sense for a variety of reasons. The core inflatable habitat has several advantages, including guaranteed structural integrity and the capacity to house critical functionality, such as the environmental control and life support system modules and the habitat's environmental sealing. The top of this center habitat will be made from the back shell of the entry, descent, and landing system. This will be utilized to reinforce and protect the inflatable structure against threats such as micrometeorites and radiation. The architecture is inspired by two ancient habitats. The Clocan beehive houses of Irish monastery sites and typical South Italian trulli residences. These are prehistoric dome dwellings created with abundant stone materials from the surrounding terrain, a true example of old ISRU on Earth. To make the interiors of the truly hygienic and clean, a plaster made of reddish clay and straw bits mixed with slaked lime was employed, similar to LavaHive's proposed method of sealing. The end result for the ancients was an earthquake-proof structure that, thanks to the thermal inertia of the thick walls, kept cool in hot weather and warm in winter. Building the habitat. When the mission delivery vehicle arrives in the Martian area, it will separate the EDL system and send it on a course towards the surface. The EDL will detach its heat shield before delivering two surface rovers and the habitat center inflatable component to Mars. The two autonomous rovers included in this payload will be utilized for 3D construction, with one centering and the other melting regolith. When the entry capsule arrives at its destination, the inflatable habitat will be deployed with the EDL back shell still attached on top. This will provide additional protection to the habitat's key core node. The two autonomous rovers will next begin preparing the region for the 3D printed parts creation. The rovers will find and collect fine regolith resources from aeolian or wind-created deposits within craters and beds before transporting them to the habitat site. The pair's centering-capable rover will start by constructing foundations for the smaller dwelling parts, which will later be completed by the lava-forming robot. The rovers will then collaborate to build habitat parts and link corridors out of in-situ regolith materials. When one cast layer has cooled, the rover starts layering more regolith sand and centers a new channel on top. This procedure is repeated until the dome is finished. Once there, astronauts will carry out final construction tasks remotely from Mars orbit or manually from the surface. They'll put in mission equipment like airlocks and safety doors that were delivered from orbit. Once the sub-habitats are physically complete, they will be hermetically sealed with epoxy coating sprayed on the inside surfaces of the sub-habitats by a rover. With the primary habitat, this epoxy will produce a sealed environment. LavaHive is a modular construction for Mars that connects core crew quarters to 3D printed sub-habitats. Thanks to Liquefier Systems Group for conceptualizing the general plan, developing an architectural idea, and creating visuals for this project. Why do we love lava? Printing with lava may appear strange, but it is actually a very elegant and straightforward method. The lava casting manufacturing technique was inspired by naturally occurring lava flows, and its practicality has been shown by small-scale demonstration efforts on Earth. The particle size distributions of the aeolian dunes and beds from which regolith could be gathered are well studied, which is the crucial issue for understanding the kinetics of any centering process. The regolith will be melted within the rover's furnace before being cast in centered regolith channels. This method of lava 3D printing has various advantages. For starters, it's stronger as a building material than thermally induced centered material. Because the 4-man astronaut team is expected to work securely within these 3D printed buildings, trust in the structural elements supporting the chambers is critical. Second, once cooled, basaltic lava will have significantly higher density than any centered material. This would have significant implications for radiation, shielding in the surface environment. The permeability of basalt stone is also higher than that of a centered process, which is frequently porous, which is an important consideration for building a hermetic environmental seal. While it may appear complicated, heating and controlling the lava itself is extremely simple. Lava is incredibly viscous, but it can travel large distances before cooling. A terrestrial Mars analog test habitat is also easily attainable, and lessons learned during the development of terrestrial Mars analog sites would be transferable to the Martian environment. So, I think we're at the end of our video. I hope you enjoyed it, and if so, make sure you like and subscribe to our channel. And thank you for watching.